We will again touch very briefly on energy balance. So essentially, we have already said several times that shortwave energy from the sun is coming in, mostly in the visible, and long wave energy is going out in the infrared, near infrared, which we cannot see with our bare eyes. So you have to figure out how much of the energy coming from the sun is intercepted and how much is going out as a whole, to look at the balance to derive the temperature. Average temperature. Okay, so the best way to do it is to think of the sun's energy coming in, and Earth as a sphere is going to intercept it as a circle, because the projection of the Earth to the light. So if you imagine a basketball or a soccer ball and you're flashing a light at it, the shadow will be a circle, and that's what faces the sun. That's what decides how much energy is intercepted as a whole. So that is pi r squared or pi a squared, where a is the radius of the Earth. That then is losing the amount because of albedo, which is, let's say, alpha. So the net energy will be pi r squared or pi a squared times shortwave coming in multiplied by 1 minus alpha, because alpha times pi r squared times f shortwave is just going back out. So that's the loss term. So if alpha is 0.3, then Earth is keeping 70%. 1 minus 0.3 is 0.7, right? This has to equal the amount of energy going out from the Earth's surface, which is a sphere. So the area of the sphere has to be considered, because outgoing long wave is going out at every point on the sphere. So the area is there 4 pi r squared or 4 pi a squared times f long wave, which is the long wave flux, which we already said is the black body radiation sigma. Excuse me, I got a frog in my throat. Sigma TE to the fourth, where TE is some effective emission temperature of the Earth. That's the black body radiation, Stefan Boltzmann law. So we know R, we know the energy coming in, we know sigma, and we can compute TE. Right? Here we are not saying anything about greenhouse effect. We are just saying Earth is receiving short wave and emitting long wave. If you do that, you get a temperature that is like minus 18 degrees centigrade, which obviously is too cold compared to the plus 15 degrees centigrade, which is the global mean temperature now, with a little bit of increase because of global warming, as we saw. Nonetheless, what we can do is then go into a 1 square meter area and do the balance to add the greenhouse effect or the atmosphere. We still start with pi r squared times flux short wave, and 1 minus alpha a is what is reaching the surface, because albedo is losing this much here. Alpha pi r squared times fsw is lost. So the surface then has to emit that much to balance the incoming short wave for equilibrium. So there is the long wave going out. Okay, so here basically the alpha is being split into alpha 0, which is the ground surface albedo, and alpha a is the atmospheric albedo, because atmosphere not only has clouds which can reflect sunlight, but also has aerosols like sulfates which can scatter and lose energy in the short wave. Okay, so that's just the detail there. All that energy is now going back out as long wave, where T0 is the temperature achieved by the surface. It's a global mean, so includes ocean, land, deserts, everything, glaciers. But the atmosphere is not completely transparent to the long wave, because you have greenhouse gases like CO2, water vapor, methane, nitrous oxide, HFCs, and so on. So it is emitting to space 4 pi r squared times FLW, which is not the same as this, plus it is emitting in both directions. If you imagine the atmosphere, which has greenhouse gases, it's emitting to space as well as back to Earth. So the surface is also going to receive, in addition to the short wave, is also going to receive some long wave from the greenhouse effect. Okay, this is the critical step. The surface temperature is going to be warmer because of the greenhouse effect, specifically because this additional long wave coming in from the greenhouse effect of the atmosphere. That's the only trick. We can solve those equations looking at energy balance. So F0 at the surface is what is coming in as short wave, and what is being lost from the surface, and what is being coming in as a long wave from the atmosphere. If we solve these, then it turns out that the temperature of the surface is 2 to the 1/4 times the emission temperature. I won't go into the details, and this will give you a greenhouse effect, which if you assume just one layer of atmosphere, you will get something like 33 degrees centigrade global mean, which is too high. So you have to add the details of multiple layers, bouncing around, clouds, multiple levels of clouds, and we will see that atmosphere is not just emitting from the surface or from the top of the atmosphere. It has a complicated emission. Okay, so once we have this equation, we will see later on that we can look at perturbations to the forcing because of fossil fuels and so on to figure out how much warming can result from that. So just to touch on the outgoing long wave, you can see that this is hardly a solved problem in terms of exactly where the outgoing long wave actually occurs. So if you remember our temperature profile in the troposphere, there are multiple layers from which outgoing long wave is escaping Earth's atmosphere. So there is a short wave coming, and then the question is, with increasing greenhouse gases, what happens? So this cartoon is trying to say that the height of the atmosphere itself is going to change because of the warming. The lapse rate is going to change, or the gradient of the temperature from the surface to the top of the atmosphere is going to change, and the height from which the outgoing long wave happens is going to change. So this is a complicated calculation, and people spend lots of time doing that. Fortunately for us, they do it, and they do it very carefully because it's very critical to follow the energy balance every single year, because we will see that the amount of greenhouse emissions, especially greenhouse gas emissions, especially CO2, is very easily and accurately and precisely measured. But global mean temperature is an average of many regions which are not all warming at the same rate, and there are even some regions which are cooling. So that's tricky to then do energy balance, because measuring radiation and energy is not that easy either, especially when you consider that the ocean is taking up some of it is getting moved into melting glaciers and so on and so forth. So it's a complicated calculation, but we can easily relate the increase in greenhouse gases to the net warming. Okay, so there is no doubt that we can, for example, we looked at the sensitivity of CO2, methane, and N2O per ppm change. So we know how the fluxes actually change, and we can actually match the averaged results. Getting the distribution is not that easy.